All right, guys. We've got this function, f of x equals, let's go 1/2 the opposite of x minus 3. Let's do this cubed, and then remove 2. Good. All right, so my question is, what's the parent function? Okay, it's x cubed. So parent function, f of x equals x cubed. Now, how do I determine that? Well, I'm going to erase all of the transformations that are taking place. So we had a 1/2 out there, got rid of that. We got a reflection there, get rid of that. Getting rid of the minus 3, that's a horizontal translation. This minus 2 is a vertical translation. And I'm left with that, right? That's my parent function, okay? That's kind of the best way, I think, of being able to recognize what is the parent function. Erase everything that is doing a transformation. Now, in order to do that, obviously you got to know what all your transformations are, where they show up, and all that kind of stuff. So our parent function is x cubed. Now, what are some ordered pairs that we know off of x cubed? Nobody knows an ordered pair?
327.
Okay, so 327. Again, you choose ones that are ridiculous.
That's the order that came on mine.
Okay, 28.
How is that ridiculous? 512.
Shut up, Chuck. 11 00 28, right? Negative 2, negative 8, negative 1, negative 1, right?
Yeah, boy.
My argument is that those 5 should be ones that we've committed to memory. Okay? That process of knowing those and then doing what we're going to go through is so much more efficient and so much more kind of fail-proof than creating a x and y table and generating values that way from this function. So when we're done, I'll kind of reiterate that concept. See what we come up with. Okay, so I want to know, as we take these parent function ordered pairs, what are we going to get after each one of these ordered pairs kind of run through this function? Okay, so you need to tell me what this 1/2 does. It shrinks. Which direction? Is it horizontal or is it vertical?
Horizontal.
Good, it's vertical. Okay, shrinks it vertical. If I removed everything, remove that negative, remove this, remove that, but leave that 1/2, doesn't that look like a C times my f of x? F of x was x cubed, right?
Yeah.
Okay, when we have a C out in front, we have that scalar multiplier, and C is between 0 and 1. We get a vertical compression or a vertical shrinking. Okay, is that all right?
Yeah.
Okay. So, put that back in. What does this minus do right there, that negative sign?
Flip it over to the axis.
Which one?
Y.
Y-axis reflection.
Are you recording that?
Yeah.
No, you're not.
Recording all your wrong answers.
No, you're not.
Yes, I am.
You don't have the thing on. It's not recording. Wait, why was that vertical?
Why is what vertical?
The shrink.
The shrink?
I don't know.
Okay, so if I just had y equals 1/2 x cubed, right? If I plug in, let's say 2. If it was plugged into x cubed to be 2, 8, right? We'll plug it in here. You get 2 cubed, which would be 8, right? Order of operations then says multiply that 8 by a 1/2, and it gives you 4. How does that 4 compare to that 8 right there? it's closer to the y-axis, right? So it's been shrunk vertically. So every time that you see a multiplier out front, every time you see that multiplier out front of your parent function, it is going to shrink it vertically if it's between 0 and 1. It will stretch it if it's bigger than 1. Yes.
Yesterday I asked you when the test was going to be. You said you'd tell me at the end of class when we have it.
Tuesday.
So is Monday a review day?
Ish. Review-ish.
Are you going to give us the review online and give us bonus if we complete it?
No.
Is it a mandatory review?
No. I gave you the review in an email.
Already?
Again.
You're not going to give it to us on,
No.
how do we know if we get the engine right?
I'll give you the key.
When?
When I get it done.
Around about what day is that?
Third period.
Today?
Yeah. Okay. So y-axis reflection. What does this -3 here do?
Right 3.
Moves right 3.
Yeet boy. I've played the You said the other day though that if somebody's happening to X inside the parentheses, it's horizontal.
Yes.
And that's happening inside the parentheses and now it's vertical. Yeah, that's what I was confused about.
What's vertical? No, this is happening outside the parentheses.
No, the X.
Here?
Yeah.
The -3?
Yeah.
Yeah, it moves right. That's horizontal.
Never mind. Never mind. It's a good thing you said a different thing the other day. Well, you did. I do have to back up my man Cole. You did.
What's that -2 do?
Down 2.
Down 2. Okay. So, we then need to take those behaviors and apply them to these points. Okay? My suggestion to you is to do them in this order. H, S, R, V. Okay? Do them in that order, and you're never going to be wrong. Okay? If you want to jumble that order, if you understand how some of those reflections and vertical translations are dependent on one another, you can jumble them. I would not do that. This is a fail-safe technique that will never fail you. Okay? It will always give you the right results. All right, so the first thing says H, so that refers to horizontal translations. Okay? So we're going to do those first. So I'm moving right 3. Okay, so if I have an X value of 3, what is that going to become?
6.
This one's going to become?
5.
This one's going to become?
4.
So it's pretty easy, right? We're just adding 3 to these X values. Okay? Now, did I do anything to the Y's? No, so I'm just going to leave them as, right now, and we'll talk about this at the end. If you want to do a couple of these steps together, and you feel comfortable enough doing that, by all means do it. But that is right 3. That was that horizontal translation. Okay? So we've targeted that one. Now let's do S. S stands for shrink or stretch. Okay, so we'll do that. So it's the 1/2. It's a vertical shrink. So a vertical shrink attacks what coordinate? The X's or the Y's? The Y's. If I'm going to shrink or stretch a graph, it's the Y values that are having that operation done to them. So I'm going to multiply all of these Y values by 1/2. So the X's do not change. Yes?
What would it look like if it horizontally? Shrunk.
Did you say shrank?
You said shrink.
Shrinked? You would have a number right here in front of the X. You have like a 2X or a 1/2X or something like that.
You know what amazes me? How I asked so many questions and he was taking notes. Amazing.
Okay, so if we are going to shrink this vertically, every Y value gets multiplied by that factor. So 27 gets multiplied by 1/2. It becomes 27 halves. 8 gets multiplied by 1/2. So it becomes 4. 1 becomes 1/2. 0 stays 0. 8 becomes 4. and negative 1 becomes negative 1/2, right? Okay, so that was the shrink by 1/2. All right, now, some of you might say, well, why did I just do those two things together? Because in that first column, all I did is adjusted the x's. And in the third column, I adjusted the y's. Why don't I just do them together and make one column where I adjusted the x's and I adjusted the y? If you want to do that, by all means do it. It's going to be more efficient. It's going to be faster. It's less writing. Okay. But we've now done that. Are there reflections? Okay. What reflection do we have? Across the y-axis. So if I reflect something across the y-axis, let's take this point here of like 2, 4, and I fold on the y-axis. What does it become? Where does it go over there? Negative 2, 4. What value changed? What coordinate was impacted there? The x. So when I reflect these points, okay, only the x gets reflected. Or I guess it changed. Only the x gets changed. So it's going to become negative 6, negative 5, negative 4, negative 3, negative 1, negative 2. And I didn't touch the y. So 27 halves, 4, 1/2, 0, 4, negative 1/2. Some of you might say, well, why didn't you just go through in this column right there and just put a negative and all that right there, right? And that's fine. I just want to give you something that is a little bit more maybe deliberate and detailed for your notes, okay? But you could have gone through there in that yellow column, that yellow line, and just stuck a negative in real quick, and that would have done the x-axis reflection, okay? I'm sorry, y-axis reflection. So y-axis reflection. Okay. So now we've done that one, and we get now to the vertical translation. So the vertical translation, what coordinates are impacted with a vertical translation? X's or Y's? Y's. All right, so the X's stay the same, negative 6, negative 5, negative 4, negative 3, negative 1, negative 2. And the Y's, okay, so I'm going to subtract 2 from this, right? Okay. So that's going to be negative 4 halves, right? Or minus 4 halves. So that's going to become 23 halves. This is going to become 2. This is going to become negative 3 halves. This is going to become negative 2. This is going to become 2. And what's that, negative 5 halves? And now, push too many buttons. Now this column are the ordered pairs that are being produced from that thing. Okay? Now, what's nice is that they are a convenient set of ordered pairs. Okay? And some people might be saying, well, why didn't you just do this? Because in Algebra 1, this is what we were taught. In Algebra 1, we were taught first graphing any new function to take x, and this is f of x or my y, and now I'm going to choose 1 here, and I'm going to plug it in. So I get then 1/2 of the opposite of 1 minus 3 cubed minus 2. And now I've got to evaluate that, right? And I could do that. That'd be great. And then I go 2. And I go 1/2. Opposite 2 minus 3 cubed minus 2. And I got to evaluate that, right? Do you see that no matter what I put in there for x, I'm going to have to go through and do that nasty evaluation every single time? Okay? What is going to stink, though, and when I do that, I'm choosing 1, 2, 3, 4, and that is not going to give me a very nice graph that models the entire behavior of the graph. Okay? And I'll kind of come back to that in a moment when we graph this with GeoGebra, but 1, 2, 3, 4, those x's, there's none of those x's on here, right, in this list here, okay? Because what we find out is that these really aren't all that useful in graphing this green function here, 1/2 times the opposite of x minus 3 cubed minus 2. It's these x values, it's these domain values that are the ones that are going to show the behavior of this graph. Okay? So, when we graph this, so let's just start with plugging in or typing in these ordered pairs. So I'll go -6, comma, 23 halves, -5, 2, -4, -3 halves, -3, -2, -1, 2, and -2, -5 halves. Okay. What do we, E was, whoa. E, what happened here? Move right 3, oh, this was -8, and I lost my negative here.
Okay.
So I apologize for that, but, and that's the thing, as you guys are plotting these, I think it's good sometimes when I mess up, because when I'm plotting these, that one doesn't look like it's having the same pattern as the rest of these, okay? If I know what x cubed looks like, right? This one's kind of out of line. So if I go put that negative back in, so I was negative, so this would be -4. So then when what do? We reflected this, became -1, -4, and then we subtract 2 from that, right? So this should be -6, -1, -6. So see if that fixes it. -1, -6. There we go. Okay. So now if I type in my function, we had 1/2 x minus 3 cubed minus 2, and we had a negative x, right? That x right there should be negative. Do we get the curve? Do we get the curve that passes through those 6 points?
Yes, sir.
Okay. And the other point, what do we have? We had one that was kind of crazy. A was kind of crazy, but that's there. Okay. So if I would have, guys, just created a T-chart, okay, where I have 1. So I'm just going to try to see if this will do this the way I want to. Let's just type in 1, comma, f of 1. So that should produce, okay, it gives me 1, -34. So I'm going to change that point to blue. And now I'm going to see, I'm going to type in 2, comma, f of 2. So what GeoGebra is doing here for me is actually going through the evaluation right here in this kind of orange text here. And then I try maybe 3, f of 3. And then let's go 4, f of 4. Okay? And I'm going to change all those to blue. Okay? Does having those blue points, does that really give me a nice, concise picture of what this function is actually doing? Okay, so I'm kind of stabbing in the dark. Okay, when I do this process of a T-chart, okay, of a table here, I'm not sure what domain values to choose so that I get an image that is representative of the actual function, the complete function, okay? And with cubics, we want that image right there. We want that behavior, okay? That point D, okay? That point D is a very, very important point, especially for calculus as we move on, okay? It's called an inflection point. It's basically where you change concavity for a function. That's going to be important for us. Okay. Does that kind of make sense? Yes, okay. You guys did the same thing when you first learned x squared. Okay, because what you knew with lines, you knew, well, if I go input for a line, I put x to be 1, and then x to be 2, and x to be 3, and x to be 4. That's going to give me enough to kind of show what the line looks like. But if I'm doing x squared and I put x to be 1, x to be 2, x to be 3, that doesn't give me, and I use only those points to plot, it does not give me enough to see the function x squared. Okay. Does that make sense to everybody? Yes, sir. Okay, I want to do one more, because I talked about this yesterday. and I said I'd show you this idea. If I start with 0, 0, 1, 1, 2, 4, negative 2, 4, negative 1, 1, what graph am I talking about here with those ordered pairs? That's x squared, okay? What if I took x squared, and I want to do a transformation to it, okay? So I'm going to say f of x is equal to, let's just say, the opposite of x squared. Let's go, I shouldn't matter here, let's go minus 3. Let's go plus 3. It doesn't matter, it could be any plus or minus. The negative does what? What's that negative transformation? Across what? Which one?
I'm the only one answering questions.
And that's fine. So I'm saying if you know, you know. Because this would be different. That's a different function than this.
Okay, is it the x-axis? No.
This is, yes, this one here would be the x-axis. Because I'm essentially applying a negative out in front. So this would look like the rule we said y equals the opposite of f of x. Okay? That's what this is modeling. This here is modeling y equals f of the opposite of x. Okay? So there's a difference there. So this, let me erase some of this. This here is an x-axis reflection. That is a vertical movement, right? We talked, and I've given you this structure of transformations to conduct that order, and I think, and I'm going to try to convince you if that is the best thing to do, because when I put them in that order, I remove all dependency in regards to these transformations off of another transformation. Okay? If I jumble them up, I've got an issue. Okay? But if I understand the issue, I'm free to jumble them up if I want to. Okay? But what I want to do this kind of backwards. Okay? I said we want to do HSR. We want to do reflections before we do vertical translations. Let's do this incorrectly and see what happens. If I do a vertical shift first to these points, okay, that's going to give me what? 0, 3, 1, 4, 2, 7, negative 1, 4, and negative 2, 7, right? So let's go with those. J-I-F, J-I-F-G. Okay, so I'm going to take those and make them blue. Okay? That's just taking the red ones and shifting them up 3 units, right? Okay? Well, now, if I do the reflection says it's an x-axis reflection. So doesn't that mean I'm taking those blue ones and I'm going to take the y values and negate them to get it to flip over the x-axis? So let's do that. Let's say I'm going to have 0. So I'll take the blue ones and just negate the y values. So 0, negative 3. 1, negative 4. 2, negative 7. Negative 1, negative 4. Negative 2, negative 7. And I get these green, not these green ones, I'm going to make them green. I get those green ones. Okay. So my argument is, well, if I've done these transformations, then these green ones should be points that are on negative x squared plus 3. And when I graph negative x squared plus 3, do those 3 or 4, 5 points show up? No, they're not on, right? That tells me that we've done something incorrect. Okay? And it's because this vertical shift, okay, is dependent on the reflection. Okay, or let's phrase it this way: the way I've done this reflection is actually dependent on the vertical shift. If I do them in this order, I remove that dependency. Okay, meaning this. Okay, I can kind of give you the visual of what's really going on here. When we shifted these red points up 3 units, what should have happened at the same time that you shift those red points up 3 units, you should take this axis, which is the axis of reflection, right? And that should shift up 3 units as well. If the axis of reflection shifts up 3 units, does it become that line right there? That would become the line y equals 3. Does that make sense, everybody? So I did this. If I do that first, then this line, I'm not going to reflect over the x-axis anymore. I've shifted the x-axis up 3 units, and I'm going to reflect over that line of y equals 3. If I take those blue dots, reflect them over the line y equals 3, do they show up then on the green curve? Yes. Okay. So that idea, that comparison, hopefully visually shows you why order matters, why I have to do these transformations in that defined order. Okay. Otherwise, the reflection is dependent on the vertical shift, and I don't want to have to think about that every time I do one of these. Does that make sense? Okay. I'm a fan of trying to learn those things because I want to know. I want you guys to know when I tell you got to go HSRV. I want you to know. Well, why can't I just do it any way I want to? And that's the idea. That's the reason. And algebraically, it's because that negative right there, that negative is not getting distributed to that 3, right? Okay. Order of operations is essentially the reason why we can't do that. Okay. Let's talk a little bit about the next topic, which is going to help maybe shorten this process a little bit if we use it correctly. If I look at x squared, but I only look at it for values to the right of the y-axis. If I take those values to the right of the y-axis and I reflect it over the y-axis and I get this garbage. Okay, now it is giving me written as a parametric curve, but don't worry about that. But I do want to change the color of it. It won't let me, so let's change this one. Come on. Okay. So I start with the blue one. I reflect over the y-axis, and I get the red one, right? Well, if I look at those collectively, is that simply just x squared? That makes sense? So if I can take part of this graph and reflect it across the y-axis, basically what we're saying is that when I fold on this y-axis, the blue part of x squared falls on the red part of x squared, right? What is that called? What relationship when you have a line that you reflect across and one part of your graph lands on the other part? Symmetry, okay? So here we have y-axis symmetry, okay? Y-axis symmetry. Let me do this. If I take, let's go x cubed. Let's only look at it for x being greater than 0. I get that, okay? If I take that and reflect that about, let's do this. Let's not reflect it, let's rotate it. Well, I'll reflect it first. Ooh. I didn't know I had this option. Let's see if this will work. 0, 0. All right, so if I take this curve and reflect it around 0, 0. 0, 0 is called the what? The origin. So I reflect about the origin, I get that thing. Okay? Which now, if I color these again, okay, that branch does it when we reflect across the origin, gives me that branch, right? Well, collectively, are those two branches the same curve? Does that make sense to everybody? Okay. Now, I reflected across the origin, and that might be a difficult task for us to think about, but the same thing happens if I were to take this and reflect it across there, and now take this and reflect it across there. Does this graph, I don't know why it keeps wanting to make everything red. There we go, that's what I want. Okay, so I started with that, reflected it to that, reflected it across the y-axis, followed that up with a reflection across the x-axis, and that branch of the cubic goes down to the third quadrant now. Does that make sense? And collectively together, they make x cubed. Okay? So does everybody see that if I were to fold on the y-axis, follow that by a fold on the x-axis, this part here is going to land on that part there? Okay? That's symmetry, right? Okay, that's x-axis and y-axis symmetry. Now, we don't like to say x-axis and y-axis symmetry because it gets too wordy. What we call this is symmetry about the origin. Okay, which you saw me, I asked this thing to reflect it across the origin a little bit ago. But go back to geometry. What does it mean for geometry? Well, for geometry, it meant this. If I've got that point right there, point B, I'm going to take point B and I'm going to rotate it. See here, rotate B around A, and I want to do it, let's do it by M, so it's going to ask me to create M. So 0 to 180. Okay, so the idea here is if I know that B is at 2,8, that is on my curve here. If I rotate B around A 180 degrees, rotate B around A 180 degrees, does it show up then still on my curve? Does that make sense to everybody? Okay, we can do that with any of these points on here. So let me just create a couple different circles here real quick. Now, we don't necessarily have to see all of these circles or any of these circles if we don't want to. I'll just keep that one. All right, so if I ask this thing to take G, D, oh, come on. I can only do, let's do it this way. Rotate those. I don't know if that's going to work. Nope. All right, so rotate this around A, M degrees. Let's rotate this around A, M degrees. This around A, M degrees. Okay, so if I do this, if I rotate them all, whoa.
What happened to B?
B, I've got too many things coded in here on accident. Okay, so that should fix it. Okay, so if I rotate all of those 180 degrees around A, do all of those end up fitting back on my curve?
Yep.
Okay, so if I understand that, and our goal of being able to graph these things efficiently, if I understand that, maybe now I don't need to remember -1, -1, -2, -8, -3, -27, because I can gain that same information just by knowing what those points in the first quadrant are. Okay? That make sense?
Yeah.
So we got some relationships here that we can learn to help us do things. Okay? Now, if this is the case, if we have symmetry across the origin, okay, that's a special type of function. Okay? If we have symmetry across the y-axis, that's a special type of function. These are referred to as even and odd functions. Okay? And they don't have to do with anything in regards to like the coefficients or numbers that are used inside the function. It has to do with the multiplicity of negative values. Okay? If I have an even number of negative values when I multiply them together, I get a positive number back, right?
That's right.
When I have an odd number of negatives multiplied together, I get a negative number back, right?
Right.
That, and we'll see maybe some of the algebra here in a little bit, that is the reason why these are called even and odd functions. An even function, though, is a function that has y-axis symmetry. Y-axis symmetry. An odd function, okay, has x-axis and y-axis symmetry. Which, going back to geometry and kind of going off of what I just showed you, that is equivalent to rotation around the origin 180 degrees, which is equivalent to a reflection about the origin. Okay. Those are all saying the same thing. There's different applications for why maybe I want to talk about x-axis and then y-axis symmetry. There might be a different reason why we'd rather refer to it as a 180 degree rotation around the origin. Okay. But they all deal with the origin, right? Okay. So an odd function starts with O. Origin starts with O, so that's how you remember which one's which, right? Odd is a rotation or reflection around the origin. So we get two rules, okay? And these two rules say that if your original function, f of x, equals f of the opposite of x, if you have this situation occurring, then f of x is even. So this is the algebraic way to check if we've got y-axis symmetry. And basically what it's saying is when you choose an x value and you get a y value back, and then you negate that x value, and you get the same y value back, so the idea here is if I look at my parabola, do I have the point 2, 4 there? When I plug 2 in right there for f of x, and then I plug in negative 2 over here, do I get the same y value back for negative 2 that I had for positive 2? Does that make sense? This is the check to see if that happens. Okay? The other rule says if f of x and then f of negative x equals the opposite of f of x, then f of x is odd. Okay? Tomorrow we'll start off looking at some algebraic equate or functions that will apply these rules to. I will. Thanks, but you don't need to have money in the office.